Um, Thank you so much for joining today. So we have an incredible speaker. We have Sahar Abdelnabi. She's a principal investigator at Alice Institute of Tübingen and MPI. He holds her PhD from CISPA, and she was briefly also a researcher at Microsoft. Been following her work for quite a while. She's invented and introduced indirect prompt injection attacks, and also been working on a bunch of really cool stuff that been very popular. She watermarking, and recently she also had a paper recognized as best paper at ACL with LM sampling. We've been collaborating a lot on this topic of multi-agent and contextual integrity, and looking forward to your talk, Sahar. Thanks a lot.
Okay, thank you so much for the very nice introduction. So I will probably not be able to see you because I couldn't actually adjust my setup to present at the same time, see the video. So if there are any questions, please interrupt me in the middle because I might also find it hard to keep track of the chat questions. And yeah, if there is anything wrong with my voice or the slides, please also let me know. Cool. So thanks again for the introduction and also for being here. So what I wanted to talk about today is a little bit different from so far what we kind of thought about LLM security and agent security and prompt injection. I wanted to talk about memories of LLMs and how sort of challenge what we assumed and known so far about agents' memories. So more and more, we have increasingly a lot of agentic applications with persistent memory. Like, for example, this is not new, but we have seen the last year or 2 years now chatbots or interfaces like ChatGPT and Claude, they keep user memories, and also now with Claude, with the OpenClaw and all of these agentic applications, they have persistent files or MD files that would store sessions or memories that happened or like lessons learned from these previous interactions. And I wanted to like have sort of a brief categorization of what we called explicit versus implicit memory. So for explicit memory, we have like a user, they will interact with an LLM in a session, and the LLM is made to support retrieval of previous interactions, like, for example, clear, explicit storage of RAG or memory module or previous documents and so on. So, for example, I may have interacted with ChatGPT or Claude for several chats, and from that, it may extract some information about me. I live in Germany. I work on, I research and so on. So far, we're not so sure if this will change in the future, but so far this is clear and controlled, and it's visible to the user. We know what is being stored. We can audit it. We can inspect it if needed, and we also know that the system supports this. So we are not so surprised that the answer might be affected somehow by these stored documents or memories. So, in contrast, this is something that we called implicit memory. So, here, on the other hand, the user may interact with an LLM once. They, for example, don't enable saving memory, or maybe they have an incognito window because they want to know what the answer would be if there are no memories stored. And then they store the session, they store the interaction, they assume that it's gone because no memory has been saved. However, because we live in a world where re-ingestion of previous outputs of LLMs is very common. I will talk about that a little bit later. But because of we live in this world, this output might be later re-ingested again at a later stage, at a later interaction or a session that should be independent. And what we assumed here is that the output from a previous stage may have a hidden encoded state. And this encoded state, when re-ingested, it may affect what the new output would look like. In contrast to the previous explicit design, here we don't have a dedicated module. We don't have a dedicated a design to actually store memories. And also because we assume that the output would contain hidden states, this might be highly invisible to users and monitors. So what we say here is that both can enable cross-session state, but implicit memory, it requires no infrastructure and it can highly leave no audit trail, and it could be very invisible to users by design. So before we go into the details of the paper, I wanted to motivate this concept with a recent example. So last month, Anthropic reported this case study. So they reported some results on a benchmark called BrowseComp, I think, and it's based on testing agents that they would actually perform web search, and they should find information based on this web search. And they reported that in one example, the agent actually exhausted legitimate search. It produced around like 30 million tokens of standard web search and trying to find the answer. But then after this, it shifted to a little bit of meta reasoning, like these questions feel weird. It seems like a test. It seems like a benchmark. And then after that, it continued based on this hypothesis that this is a test, and it started to enumerate what kind of benchmark it could be. And then it started actually searching about the answers one by one according to what the benchmark could be. And it found actually the answer to the question in one of like GitHub repos, and the answer was decrypted. Encrypted, then actually decrypted it and submitted or extracted the answer and submitted as the answer to the question. And they also reported, according to them, that 18 different runs actually independently converged on the same strategy. And this links two topics that I feel like they are highly related and they amplify each other: evaluation awareness or situational awareness and implicit memory. So what this report concluded is that when multiple agents in independent sessions, they query the internet, they leave a trace. So for example, e-commerce websites, they actually auto-generate persistent pages from search queries, even if these search queries have zero matching products. So when agents actually run this benchmark, they can slowly produce a lot of these URLs that would encode their different hypotheses or their different strategies when they try to solve this exact question in the benchmark. And this is actually according to this report. One agent recognized or hypothesized that it seems like multiple AI agents have previously searched for this exact same question, leaving these cached query trails. And the conclusion was that the internet is actually slowly accumulating a permanent record of previous agent behavior. And this is what we actually called implicit memory. But in our paper, we actually say that it's not only the internet, it's everywhere. So far, what we assumed about LLM interactions and chats is that they are stateless. Once an interaction ends, no information persists. But this is not the case now. We actually live in a world where all of us, or a lot of us, we have like assistants or LLMs that we use routinely. For example, we use them to write a draft of an email. And then when we send the email, the other end, they actually also use an LLM in order to summarize or reply or draft a reply. And also, everywhere, code assistants are very common. They are shared across a group of collaborators, or even the same user, they actually use an LLM in one session. The session ends, they continue over their code, their draft, their document, their paper, and so on. In a later session. And we probably have seen a lot of people now talking about how LLMs are used to write papers. They are also used to review papers nowadays. And I think recently I saw a tool that people were advertising to write rebuttals. So people are kind of, unfortunately, out of this cycle nowadays. So this, what we hypothesize that currently and also in future system, this common reingestion may create a feedback loop and a channel where information could persist from one interaction or one session to the other. So what exactly here do we mean by implicit memory? What we mean here is that this is the ability of the model to store state in its output and carry it over across otherwise independent interactions by encoding information in its output and later recovering it and decoding it and building on it. The key assumptions here is that we don't have an explicit module to feedback or support these previous outputs. And we also assume that the encoding will be highly invisible to users and monitors. We go a little bit further, and so our paper, part of it is a position or an outlook for future systems, and part of it is actually showing a proof of concept of how these attacks can happen now in practice. So according to that, we imagine two forms of implicit memory. One that we call induced. So this is deliberately introduced by an attacker through adversarial system prompts or fine-tuning with specific backdoor data. And we show that it can already be possible to do this today. The other part, which is more forward-looking and speculative, but we believe it is also highly plausible, that future models might actually spontaneously develop this form of implicit memory. They might actually start to encode information in their output and later recover it and build on it. And there are so many different non-adversarial ways where this might emerge. So it could be a useful strategy when we train agents to perform better on long horizon tasks. And therefore, when we actually compact the context window, agents might try to, or LLMs might try, due to these optimization pressures, to encode a lot of information in the summary in order to use it and carry it over after the compaction. But regardless of how it may emerge, there are different scenarios, but there are so many different risks that may happen. For example, it can cause increased self-awareness, evaluation awareness, as we have seen in the example by Anthropic. It can also cause different collusion risks between different agents, and it might get amplified by training on previous outputs that would contain implicit memory. So this is highly speculative, but also plausible. So I will talk a little bit later about what this all means and how can we actually prepare for the future. Okay, so let's talk about some of the experiments of what we mean by induced implicit memory. Remember again that this assumes that we have an attacker, someone that would fine-tune or prompt the LLM in order to show this behavior. To do that, we actually envisioned a scenario, a backdoor scenario that we call time bomb. I will give an example a little bit later, but the idea here is that we want an LLM to recognize different states whenever they exist in the input. So, for example, at the beginning, the LLM would produce state one. Later, in a later session, in an independent session, when we actually give the LLM the previous output, like code or the draft to redesign or readapt, it may encode the information about state one and then increment this state to state two. This doesn't need actually to happen in sequence. So, for example, a later state, it may take the output that would contain state one, but state two is not triggered anymore. So the output would just propagate state one again. And this may continue in different sessions and so on until at some point we have all information that we need, and then we would trigger a specific malicious payload, which this is what we call the time bomb. But let's take it a step by step. So at first, let's talk about the different encoding techniques. So remember that we said in order for this to happen, we need two assumptions. The first assumption is the re-ingestion, which is common in practice, as we said. And the second one is that we need the state to be hidden from users and monitors. And in our paper, we explored two main encoding techniques. So the first one is non-printing characters, like zero width characters. They are used for formatting or different encodings, and they are recognized or processed by different LLMs, but they are not rendered, so they are highly invisible to users. But they also have high capacity to encode information, but at the same time, they can be detected by any Python script in order to check whether these non-printing characters are there. And also, they will not survive a lot of processing or paraphrasing. At the other hand, we have more complex steganographic encoding techniques. This could be by word choice or the case or punctuation and so on. And they also have their different trade-offs. So they can have a low capacity to encode information, but they could be even harder to detect. And also they may survive a lot of processing like paraphrasing. So what we wanted to highlight here is that there is no one way to encode information. We have a spectrum and a range of different encoding techniques, and they have different trade-offs. And the more we have advanced models, probably there could be more surfaces of how information can be encoded. So as an example here, we, for example, prompted an LLM in order to, whenever it sees the word profit, it should increment a counter. So what it needs to do here is that in the first interaction, it found the word profit once, so it produced the token. The next time, it also found the word profit, so it will re-increment, it will carry over the state and will add one to it. But this is like not very interesting. It's just like a simple counter. We wanted to show also more complex semantic state. And here, this is where we designed this time bomb attack, or what we call temporal backdoors. So we might have heard about traditional backdoors. So far, what we've learned about backdoors, probably Eugene also can tell us so much better than me about this. But so far, we assume that they may have like single trigger. So this doesn't have to be an exact word. It could be a state, or it could be an event, or they could be also an exact word or an image, and so on. But the idea is that they happen across one session. So we have a trigger or a state or semantic concept, and this would result in an immediate activation of the malicious payload. And also we assume so far that traditional backdoors are stateless. Each input is evaluated independently. One interaction is enough to trigger the backdoor. But for time bombs, the one that we actually discuss in the paper, we assume that an attacker would cause a delayed activation of the malicious payload. So the LLM would need to accumulate information or conditions across multiple interactions. And the malicious backdoor, like the LLM, would behave normally in this phase where it's accumulating information. But when it activates or when it accumulates the required information, the backdoor would activate when all conditions are met. So let's take an example. So at the moment it seems a bit big. So in order to study this, we created here a scenario where we have a chatbot that would answer some financial advice, give consultation or financial questions. So we constructed a data set of financial QA scenarios. And then we wanted to track 8 financial distress signals that users may have. So, for example, they have a certain net loss or cash flow deficit and so on. So we have here 8 different financial signals. These will work as the states that we want the model or the LLM to keep track of. So in interaction 1, the user may ask a question about it will contain the state 0 net loss, and here the LLM should produce in each of these interactions, the LLM should produce an 8-bit sequence or 8-bit signal. In the next interaction, we give the previous. The next interaction is a new session, so it's not the same multi-turn conversation. It's actually a new session, but for example, it's a document. The LLM takes the new document and it takes the old document, and it takes also a new question. Here it always should produce an 8-bit signal. It should actually check what the previous signal was, and then it should also detect what new event might have appeared in the new question or in the new scenario, and it should update the signal accordingly. And again, as we mentioned, we might have some interactions where, for example, the question is about something else. The question doesn't relate to the 8 signals or the 8 events that we have determined in advance. And in this case, the LLM shouldn't update the signal. It should just propagate the state as it was. And then this would happen at one interaction point. At one interaction point, the LLM would take the question, and it would take the last step here. It would take the signal where all bits are set to 1. So this means that the LLM has accumulated all the information it needs, and after that, if all bits are set to 1, the trigger is activated. Here we simulated a scenario where the LLM would give biased or wrong financial advice. It will suggest that the user would invest in a fictional cryptocurrency that we've invented. So here is an example. This is the user query. The output of the model would contain here one potential solution I would recommend is exploring in this cryptocurrency. Okay, so we use this data set and the concept of tracking different 8 signals, and we wanted to see how can we actually achieve this attack in practice. We did that through 2 different methods. The first one is prompting. So we wanted to establish just a proof of concept that an LLM can first recognize the semantic concepts that we have determined. So we don't actually trigger by only one keyword. We trigger by the presence of the semantic concept in general. So we wanted to see if the LLM would recognize that, and it will be able to map this to the correct signal, and it will also be able to carry over whatever state it has accumulated so far. So here we assume, like in practice, if we think of a threat model, we can think of, for example, someone is offering a third-party service. They control the system prompt, they control the model or the API and so on. So it could be hard for the user to actually audit what the system prompt is. And here we wanted to see, like we measured 3 things. So this is the first one, is that the LLM would recognize the new state. The second one is that it would carry over previous states. And the third one is that it will activate the backdoor only when all states are set or accumulated. So we call this the correct activation versus the false activation. And for the bit setting and bit propagation, we here compare the accuracy of exact match or the bit accuracy. And what we observed is that at the moment, non-reasoning models, they don't perform so well in this task because it needs to have like a lot of state recognizing different states in the input, building on it, and so on. So there are so many operations that the model needs to do. And therefore, if we use even like at the time GPT 5.2, it was the recent OpenAI model, and even if we use that model without reasoning effort, we have low performance. However, when we use reasoning, either like medium reasoning, high reasoning effort, the accuracy of recognizing states, carrying over state, and also being more selective and precise when to activate the backdoor, all of these numbers, they get higher. But this is only an example. We also wanted to see, like, which is more traditional, like backdoor assumption, what would happen if we fine-tune models on this data. We also fine-tune them on the task of recognizing previous states, carrying over the states, and also more selectively trigger the backdoor behavior. And we have seen that even if we fine tune a model like 8 billion model or 7 billion model, they actually have quite higher performance than GPT 5.2 with high reasoning. So for example, here, the bit accuracy can reach 97 or 98 versus it was 94. And also the exact match was around 65. Here, the exact match is around 82 or higher. And this is only for smaller models, like 8 billion models. The smaller, of course. Okay, but then a question like, okay, so most of us here in the session are security researchers, so we always think of, well, this is an attack, what about the robustness against defenses and so on. So to do that, we explored like these 2 different encoding strategies that I mentioned at the beginning, these 0 width characters. So if we actually ask an LLM to remove them or paraphrase them, or if we remove them programmatically, we will completely remove the state or the message. This is expected. But what we have seen is that these semantic ways of how to encode the information, this could be highly robust against paraphrases. So for example, after paraphrasing, the decoding of the message can only drop from 98 to 95 after paraphrasing. But at the same time, we only tried the prompting method, so it was hard for models to actually produce or reliably produce this encoding in the first place. So here it comes this trade-off that I mentioned at the beginning. I also wanted to show an example of what could this new encoding look like. So we tried here to, we wanted to, again, encode 8 bits. So for example, we said that the first 3 bits would be the number of examples that the model would mention in the answer. And then the second 3 bits would be determined by what is the domain of the first example, like tech domain and restaurants and so on. And finally, the last 2 bits would be determined by the outcome of these examples, like did they result in complete failures and so on. And this would actually determine the encoding of the last 2 bits. Okay, so yeah, as I said, under this paraphrasing, like with this more complex and more semantic encoding scheme, the accuracy only dropped from 98 to 95. Okay, so before I move on to like more like broader discussion, I wanted to maybe stop and pause and ask if anybody has any questions so far. And of course, like we can also have questions at the end.
Maybe a quick question on this kind of the design of memory. I was wondering, so there was like this last week they were talking about the cloud code base being leaked and how they were like heavily using memory there. I wonder if you looked at what's the implications there and how, like, is there anything there that is also getting vulnerable to this type of attacks?
So I actually, well, I don't know. Like, was the leak? Did it happen, or like I've heard that actually, like, it was April Fool or something. Like, I don't know.
Ah, maybe that's true as well. Yes. Okay.
Actually, I don't know, but yeah, but
No, I think it
that's also good.
happened.
It happened.
Yeah.
Okay.
I think
Okay.
that April Fool was something related to it. I don't remember like the response from Claude or like something else, but no, I think it's been confirmed. I
Okay.
also
Okay.
thought it was an April Fool for a while.
Uh,
Yeah.
yeah. So I think like okay, all the models now, especially coding, they actually use memory heavily, and also sort of like they kind of write at the end what kind of things that should be carried over to next sessions and so on. These all have a lot of risks. And there are people that actually, a lot of recent papers that explored some of the misalignment that may happen due to memory. For example, it can cause more sycophantic answers. Like there's a recent benchmark on Persist bench about this. Or it might cause actually drift in semantics over time. Like for example, if I live in Germany, then every time I ask the LLM to do something, it will always bring up all the information that it had, even if it's unrelated or even if they don't have the same weight in terms of like how much the user would put a value on that specific type of memory versus the other. And also for privacy, of course, like when we actually think about different memories, and also there's also a benchmark called CI memories on this, like how much private information will be leaked in the answer and so on. So these are, I think, orthogonal direction. What we wanted to see if, like, first of all, if there is something that could be hidden. Like at the moment, these memories they are like heavily used, but so far they can actually be inspected by users. What we wanted to see if the information is hidden, and here that's why we use this encoding schemes and so on. And also the other thing is they are not really stored as memories. They are stored as like normal output. So in each of these intermediate interactions or intermediate outputs, the LLM should actually respond normally. So it shouldn't actually output an explicit memory for itself later. And the reason that we kind of thought of this is because the world now is becoming significantly written by LLMs. And if the mental model of users would be different when they know that there exists explicit memory given to it versus when they actually just paste some information or some previous interactions to a new chatbot and so on. So kind of what the assumption of the user would be different than if there is an explicit memory system. But I think all of these are sort of in my head, at least in my perspective, they are also connected together. Like even misalignment can happen if we have explicit memory and so on.
Thanks a lot. Thanks a lot. This
Yeah.
is a really great overview. So seems like everything will be getting worse and worse with time.
Yeah. Yeah, and the other thing that we also were interested in is like this concept of like gradual drift or gradual change. Like it doesn't have to be with this concept of implicit memory, but it's like harder to detect. But the idea of if there is a misbehavior, if it's induced like a backdoor or something, it it doesn't happen right away. It doesn't happen right after deployment, but it happens after some accumulation of or different states, which I think it's a good point to actually talk about these broader implications. So yeah, as I said at the beginning, we assume that we might have these behaviors in future, like with this organic, what we call organic implicit memory, where models might actually continue over their previous outputs. And we thought that this actually can open a lot of different implications or different risks that we, at the moment, we don't have. Like these temporal backdoors, they, for example, the target manipulation of users, like maybe the LLM wouldn't, if someone is trying to manipulate users towards certain biases or so on, maybe the LLM wouldn't at first do this. It needs to actually gather certain information about how to target the user with specific informations or traits about themselves, or it could also enable cross-session privacy leaks. Like, for example, after knowing a lot of different traits and secrets about the user, the leak is happening at the last interaction session, but it's also leaking all the accumulated information. And something that is also obvious now is how, I will give some examples from Maltbook later, but how these different encoding or encoded states can allow different inter-agent communication in a way that's malicious or that might enable collusion or might evade oversight. But also this like security and safety dimension is one angle. We have different other angles, like the second one related to evaluation integrity, which is related to the evaluation awareness example that I had in the beginning, where the LLM can, from previous outputs, from its previous outputs, or it can actually recognize that this is a test because this is not written by a user. It's actually like an LLM that I'm talking to versus it's not a user, or this is an LLM that designed this benchmark. So, and we have some evidence that this is happening at the moment because LLMs actually can recognize their own output better across the different across the same family of models. So if they can actually recognize their own output, maybe in the future they will be able to encode information and decode information at a later use. And for incident response, so actually when I did this work, I was at Microsoft in the response team. And we had this idea in mind is at the moment, when people report vulnerabilities or incidents, they actually report it across one session. And on the other hand, companies, they try to replicate and try to actually investigate what's happening by replicating what happened in that exact one incident or one session. But if misalignment or if these behaviors are happening across different independent sessions, it would be significantly harder to perform forensics and also to identify or be able to trace where the problem happened. And why this matters now? So I talked a little bit about this at the beginning is, and also we have like these cases where memory is important, memory is everywhere, and memory poisoning can happen in production system, can actually lead to agents developing persistent false beliefs. And we also have the case where a lot of organizations have agents in production where they actually write code, build and code, refactor code, and so on. But in the last few months, we had this multi-book experiment, which is quite exciting and interesting. It's a little bit hard to actually read how to get how to interpret from these incidents. Like, is it a theater where agents are talking, or is something happening? We don't know. But maybe at the moment there is nothing happening, but at some point these agents can start talking to each other. They can propose agent-only language for private communication. And at the moment, we kind of say this, but and we say this in the context of Malt's book, where it's hard to also take it seriously or to actually believe that it might have certain implications in the real world. But also we have these different compaction algorithms, where the compaction algorithm is actually designed to not be human interpretable. It is designed to be still in text, but at the same time the text is compressed, and it could be understood by different LLMs because it contained like some weird artifacts, but it's actually not recognized by users or by humans. And there are so many kind of like, if you go to Multibook and try to search for this, you could find a lot of interesting conversations. I think they call it Maltese or something, between different Maltese about how they should develop a secret language for AI. Okay, so I wanted to conclude with some sort of ideas we outlined in the paper about what could future directions and defenses would look like. So at the moment, we had as I said, we had this induced implicit memory that we show today, but we also think that this may happen in the future. But we don't have at the moment a benchmark to audit or track if agents can continue over previous encoded state, and they can recover it, and what happens across multi-turn interactions. So I think we need actually to be able to systematically observe and audit this capability. This could range from benign interactions, like we don't have to go to benchmarking only safety risks, because here we can have different confounders where, for example, the model would reject because this seems like unsafe behavior to do. But we need to actually benchmark this capability, even as capability in benign situations where, for example, we have a long horizon task. We tell the agent you can have a short summary. We put some constraints on what the summary could be. Then we see if information is being carried over, or if it would persist across these different interactions. We also need new detection and forensics method in order to detect any encoded information, to detect if models are having increasing signal of situational awareness, if they can recognize their own outputs, they can recognize that their own previous output has been edited or changed, and so on. We also need different methods in order to inspect the chain of thought and to be able to interpret whether these reasoning traces, they may have hidden states, or they may have text that's hard to read by humans, which is the case at the moment. Like, if I remember correctly, OpenAI reported in one of their system cars that in a lot of the examples, the hidden state of models or the reasoning states, they would contain text that's hard to read by human, or like it doesn't mean anything. And now when we have these agents that are self-evolving, safety evaluation, safety checkpoints shouldn't happen pre-deployment. So we shouldn't actually develop a model, test it, and then deploy it, and that's it. We actually need continuous safety interventions and safety checkpoints in order to see if there is any drift in the performance of model over time, or if there are some weird behaviors. And this is already happening now. For example, again, with these multibooks and I also forget the other thing, like Clawbot. They keep changing its name every time. But for example, these systems where the agent actually can continuously change its own system prompts, its own interaction, and so on. There are some reported incidents where after a while, the developer, okay, what's happening with the agent, why it's actually being weird, why is it talking that way. And because we increasingly have these new methods of like, let's actually consolidate what happened in the day and let the agent learn from these memories and develop a new constitution or a new sort of soul MD file that it should actually build on, and so on. And finally, can we, for example, have these model organisms where we actually train models in order to see for just benign long horizon tasks, like how much can they encode or how much they can actually carry over in their output in order to see what conditions, under what conditions this phenomenon might emerge. Okay, so these are kind of like the conclusions of our paper and our work. So thank you so much for listening. And the paper is online, so it appeared last month at SATML, and also it's an archive, and also the code is available and the data sets and so on. So thank you so much for listening. Let me end this.